Hello everyone, I'm Mahmoud Hamandi and I will be presenting this paper with my colleague Dariusz Horla. The paper tackled the optimal tuning of the lateral dynamics parameters of aerial vehicles with bounded lateral force. To introduce our topic, let us first introduce bounded lateral force platforms. A bounded lateral force platform, or BLF for short, is any platform that can apply forces both along its vertical axis and along its lateral horizontal axes. This platform class groups many designs, such as quadrotors with tiltable propellers or tilted propeller hexarotors, which we will focus on in this paper. Our study relies on the Tiltax platform shown here, which is a tilted propeller hexarotor with each propeller tilted about its radial and tangential axes. We should note that we use the name BLF both for the platform and the corresponding BLF controller. Such a platform modeled as BLF has multiple parameters that dictate the controller's performance. First, the controller requires the estimation of the platform's mass and inertia matrix. Usually, these parameters can be easily estimated from the platform model. Moreover, the topic of estimating these parameters online has been thoroughly studied in the literature. The controller also requires the tuning of the gains of the attitude controller. The attitude dynamics are assumed independent of the rest of the vehicle's dynamics and only require the knowledge of the inertia matrix. Furthermore, these attitude dynamics are fully actuated and show no real limits in the BLF model. As such, these also could be tuned online with methods demonstrated in the literature. Next, the BLF model requires the choice of the maximum intensity of the lateral force of the platform. This parameter merits further explanation. We show here a presentation of the force set at hover of the BLF platform shown earlier. We also show the maximum intensity of the lateral force. This parameter changes while changing the applied lift and the applied moment. As such, it is very difficult to estimate online. Rather, the BLF controller requires the input of this parameter. The estimation of this parameter affects the entire dynamics of the platform. Even for a fully actuated platform such as the Tiltax, if this parameter is chosen small enough, the platform will behave as an underactuated platform and there will be a coupling between its position and attitude dynamics. On the other hand, if this parameter is chosen large enough, the platform's dynamics are treated as decoupled. However, the controller risks reaching the limits of the actuators. As such, it is not straightforward to estimate the maximum intensity of the lateral force. The BLF controller also requires tuning the gains of the position controller. These gains can be split into the gains of the vertical dynamics and lateral dynamics. The vertical dynamics are independent of the rest of the parameters and can be easily tuned with standard tuning algorithms. However, the lateral dynamics are in fact coupled with the choice of the maximum intensity of the lateral force. Since the bounds of the lateral force affect the lateral dynamics, they affect the choice of the lateral dynamics gains. As such, these gains have to be chosen in an optimal way following the choice of the lateral bound parameter. As such, in this paper, we aim to study the interplay between the maximum intensity of the lateral force and the gains of the lateral controller. Moreover, this paper aims to provide a systematic method to optimize the position gains following the choice of the maximum intensity of the lateral force.
The optimization algorithm that is used to tune the position and velocity gains for a given value of the bound on the lateral force is an implementation of the Model 3 OptimTune algorithm presented in one of our prior papers in Sensors Journal and requires only a measurable metric of the performance of the controller in order to work. A complete analysis of its convergence can be found therein. The method offers a fully automatized tuning of the gains by iterative contraction of the ranges in which the optimal, that is, the sought values, belong to. The novel optimization procedure presented in the paper needs no mathematical model of the dynamical system, on the contrary to the tuning methods available in the literature, either related to a time-consuming particle swarm-like optimization or application of neural network solutions, training sessions, and high computational burden, all based on an analytical model of the system. In addition, the cost function value can be calculated on the basis of experiments for a given reference primitive signal, which is tracked in a given time horizon and can be obtained directly from the measurements. By repeating the reference signal primitive and observation of the performance of the system, the optimal solution is sought in an iterative manner by the use of zero-order minimum seeking algorithms, which require only cost function values. The core assumption in the tuning algorithm is that the cost function is unimodal during a line search. This is a common case for control systems, where either one has a set of local minima or a strong global minimum to be found. The method has a natural escape property due to the mechanisms shown on the next slides. For an initial range stipulated by the user, or for the range taken from the previous iteration, two symmetrically spaced intermediate points are taken to evaluate the cost function. Here, the evaluation of the cost function is related to a single stage of the experiment for a given set of gains, and the cost function itself is the performance measure. After a pair of experiments and cost function evaluations, the range is contracted so that the minimum remains captured within the range just by comparing two performance measure values. A single evaluation of the performance measure related to the cost function is, it has been said, looped and comprises tracking the reference primitive stage, altering the value of the optimized parameter, and the interval to allow possible transients to decay to start the next measurement session. After a pair of measurements, the decision is made how to contract the current range. The stopping criterion is naturally related to the length of the final range, which can be understood as a tolerance of the uncertainty of the location of the minimum, presented here in reference to a relative length of the final range. For example, when we are satisfied with the final range in length less than 5% of the initial range, the number of iterations for this parameter is 6, which means that 12 performance indices values need to be collected. When a single tuning procedure for one of the gains is finished, it becomes frozen, and the optimization is carried out for the remaining parameter. The one parameter search time consumption is defined for the tolerance Xi, with resulting number of iterations denoted as capital N. As can be seen, the overall optimization algorithm is a combination of two nested loops, an outer loop defined in the slide, and the inner loop, which is a single parameter tuning. At all times, one parameter is tuned at a time, resulting in the optimal gains, which are assumed to lie in the center of the final ranges. To sum up, the algorithm is started with initial ranges, presented here in a two-parameter tuning framework by a dashed box. And along the way, the ranges get contracted to give eventually the final region where the optimum lies. In the application for the purpose of this paper, we have selected the cost function as a weight sum of the history of absolute position errors along a horizontal axis of movement, and the angular errors with a way defining the contribution of the two components. The tuning goal here is to find the optimal controller gains that improve the lateral trajectory tracking, while the platform remains as much as possible horizontal, thus exploiting at best the lateral force capability of the BLF platform. The slide shows contour plots of the two components of the cost function at two allowed lateral force values. The position in the left column and the angular error functions in the right column are shown separately to understand the effect of each of the performance indices on the presented tuning scheme. This figure shows that as the bound is increased from 2 to 8 newtons, the lateral position error component decreases slightly for almost all values in the given range, and the number of local minima slightly increases and the position error changes moderately. On the other hand, the angular component shows a different behavior where it can be seen that the number of local minima increases substantially for a greater bound. In addition, as the bound is increased, the values of the angular component decrease substantially. This feature can be vividly seen from the different scales on the corresponding contour plots in the right column. Finally, along with the increase of the maximum allowed lateral force, the angular component values decrease considerably, what is similar to the effect of increase in the weight. We have conducted an experimental campaign to demonstrate the tuning of the proposed algorithm and to show the relation between the chosen lateral force bound and the performance, as well as to study the effect of the angular component on the tuned gains. A single reference primitive comprises back and forth motion in the x-axis, while the controller is asked to keep the platform flat. In the following slides, the evolution of the tuning algorithm is shown for a given lateral force bound and the angle contribution weight. During the experiments, we see that for a given reference primitive, the cost function shown below increases and the error accumulates underway. The black line in the middle plot shows one of the gains frozen and the other gain tuned. The shaded area in red in the middle plot shows the uncertainty interval, I mean the considered range between a pair of the intermediate gains. When a single performance value is collected, the reference primitive is again fed to the control system to move to the next iteration. We can see that the cost function decreases with the run of the algorithm, and that when one of the gains has been tuned, it is held constant over the next stage and vice versa. The procedure is repeated twice to fine-tune the gains, resulting in 48 iterations, each at 5% accuracy. Obviously, the resulting gains offer optimal performance and minimization of the cost function.
Following the above experiments, we conduct a systematic experimental campaign to study the variance of the position gains for different values of the maximum intensity of the lateral force. We conduct these experiments for two values of Q, and we show here the statistical data of the experiments repeated thrice. These figures depict that as the lateral bound increases, the optimized Kp increases and the optimized Kv decreases for both Q values. In the case of Q equal to 300, the contribution of the lateral constraint is reduced substantially, leading to higher optimized Kp and Kv values, as the optimization allows for more aggressive position tracking without taking the angular error tracking into consideration. Finally, we would like to thank you for attending this presentation and would like to thank our sponsors for their support.